Okay, right. So responsivity should be higher and quantum efficiency should be higher. Okay, these two are very, very important for any photodetector. Okay, right. So here in our PN photodiode, so PN photodiode, the depletion region is very less area compared to device area. Suppose this much device area is there. Here only the depletion width is very less compared to this total device area. The depletion width is very less. So in our photodiode, what is the active area? Please tell me what is the active area in any device? Which electrons are where generated electrons in which place are useful? In which region electrons holes are useful to producing current? Suppose here also electron holes creating, in the depletion region also electron holes creating, in the bulk region here also electron holes creating, P N. Okay, so which region electron holes are creating a current or causing a current in a circuit? Which electron holes? Please tell me here. Is it clear? Question is clear. Suppose you are, when you shine the light here, okay, when you shine light here on the device, on the photodiode, we are creating electron holes, right? We are creating three regions. One is bulk region of P semiconductor and bulk region of N semiconductor and one is junction. Okay. So in these regions electron holes are creating, which electron hole reason for generated current or produced current in a circuit or device? Which electron holes pair useful for producing the current? Where, which region is useful?
Depletion layer.
Yes, very good. So you know, but why you are not answering, I don't know. So most of the know, but you are just listening or just silent, I don't know. But in the bulk region, recombinations happening. Okay, the electron hole recombination happening because there is no electric field. There is no electric field. That's why these electron holes are recombining. So in the depletion region, we have electric field. That's why we are separating holes to P side and electrons to N side. These electron holes, separated electron holes by electric field are useful. So in PN junction, in PN photodiode, the depletion region is very small. Okay. So here small area means width, please mute. Depletion width is small. Okay, just right. I am writing. W is the depletion width is small. So small area means only few electron holes will be created or generated. So if less electron holes created means less current also less. Okay, current also less. So that's why if you use only only PN photodiode, the depletion width is less. So we are creating only few number of electron holes. So current also less in this photodiode. Response current is less means nothing but responsivity is less. So this is one drawback. So depletion width is very less. So the drawback of PN photodiode is less responsivity. Responsivity is low. Why? Because depletion width is smaller compared to complete width of this device or complete width of the semiconductor. PN and semiconductor. So here our because why? Because why this is our depletion region only active area. Please mute man. Who is that? Please mute. So our active area is only depletion region 66. Mute చేయమ్మా ఎందుకు అన్మ్యూట్ చేస్తున్నాం. So our active area is only depletion region. That means whatever electron holes generated in the depletion region only useful for the current or main we can create only less number of electrons. If less number of electron holes creating means less number of current will be produced. That is one drawback of this photodiode. So here, how to increase this depletion width in a PN photodiode? Which way we can increase the depletion width? Please tell me how we can increase the depletion. Suppose you want more current, your depletion width should be higher, right? Your depletion width should be higher. Then more number of electron holes will be created. Then this is useful. More number of electron means more current will be generated in a circuit. So how you will increase the depletion width here? Please tell me. Suppose if you take a small bowl here, suppose this is 1 liter bowl. So here only 1 liter water you can pour here. Suppose if you take another bowl, this is 2 liter, right? You can fill that 2 liter water here. So if area is large here, you can pour more quantity. You can pour more quantity. Here in the first case, quantity is this volume is very less. Okay, volume is very less, so you can pour less quantity of water here. Okay, you got it right. So in photodiode also here, P and photodiode, especially P and N photodiode, like that our active area is less, smaller, or you can say smaller value. So less electrons only created, less holes only created. So how you will increase this depletion width here? Please tell me, please answer this question. How can you increase the depletion width? Please answer this one.
By increasing electric field.
Yeah, very good, excellent. So that we can do it. Okay, by increasing electric field, we can increase the negative bias. By increasing electric field, that means you have to apply reverse bias voltage. When you increase reverse bias voltage, the electric field increase. Why this electric field is increasing? Because if you apply reverse bias voltage, more number of holes attract towards the negative terminal and more number of electrons attract towards the positive terminal. That means the depletion region will increase in a semiconductor. But this will also, we will extend up to certain value. Okay, we will extend up to certain value, because if you keep increasing, we have studied reverse breakdown voltage. Reverse breakdown voltage. If you keep increasing at certain time, certain voltage, the device will damage. So up to certain voltage only we can increase that depletion width, right? Beyond that we cannot increase. Beyond that we cannot increase. So suppose here you have a applied, okay, here you have applied reverse bias voltage. Okay, reverse bias voltage, that means, sorry, this is P and N. So holes will attract and electrons will attract towards the positive and this negative terminal, so that this depletion width will increase, right? So this will also up to certain voltage only. This is, we are applying reverse bias, right? Reverse bias voltage in the battery. So up to certain voltage only we will apply the voltage. Beyond that there is a breakdown voltage. Okay, that means breakdown voltage means if you keep increasing reverse bias voltage, electric field, at particular voltage the device will damage. So using this one we can increase up to certain value only. So for to overcome this problem, to overcome this drawback, what we are doing is, next one, we are inserting a intrinsic layer. Okay, intrinsic layer in between P and I regions. P and I regions. We are adding one more layer, that is intrinsic. Intrinsic means it is a pure semiconductor. Okay, pure semiconductor. We are not adding any dopant atoms or any acceptor atoms. Okay, that is what that is what this PIN photodiode came. Okay, PIN photodiode. Already we have PN photodiode, but because of this drawback, low responsivity and low depletion width, low active area, and also recombination loss also high in PIN photodiode. Because to overcome these drawbacks, we another photodiode we have developed, that is PIN photodiode. This P, we have just inserted I layer in between P and N layer. Okay, once you inserted eye layer, what will happen? We will see that is PIN photodiode. Okay, so why we are going PIN photodiode? You got it right. Why? Because in PN photodiode, depletion width is smaller. Using electric field, using reverse bias voltage, we can increase depletion width, but this will also up to certain value only. After that, if you keep increasing electric field or voltage, the device will damage. Okay, certain value only we can increase this one. So if depletion width is small, our generated electron holes are less. So current also less. That means responsivity and quantum efficiency are less are low in for PIN photodiode. To overcome this problem, we are going to PIN photodiode. Now we will see how that will work. Okay. This is also one of the important topic, PIN photodiode. Nowadays everything is just PIN photodiode only. Okay, PIN photodiode. So here just what we are doing here, this is just like same as it is a PN diode only. So just I am trying again this one. Here P region and here N region, two semiconductors in the middle, intrinsic region. Okay, intrinsic. I means intrinsic. That means without any doping, any this thing. Okay, pure semiconductor. It's a pure semiconductor. Okay, so in the middle up to here, let's take a this P type and this is N type. Okay, this is P and N type. So here we know holes are the majority. Once holes will diffuse here, it will negative charge will induce, right? Negative charge will induce. This is depletion region towards this side, and here also electrons are, when electrons diffuse here, it will leaves a positive charge density. Okay, this is because of this one. So here in this intrinsic layer, the main feature of intrinsic layer is we are not doping any atoms, doping atoms or impurity atoms. We are not adding any impurity atom. So electric field is constant this layer. Okay, constant in this layer. So that means electric field extend throughout this layer. Electric field is extending throughout this layer. Okay, up to here. Okay, here also plus to minus, electric field direction is plus to minus. So inserting intrinsic layer in between P and I layer, we are extending the electric field throughout the I layer. Okay, throughout the I layer. That means compared to PN photodiode, using I layer, we are creating extra space or using more area, more active area we are creating. Inserting I layer, we are creating more active area, and also in this, after creating more active area, suppose if you shine light here, similarly like last discussion. Okay, so here also we are shining the light, the photodetector function. So when you shine the light in the bulk region, also electron holes creating, in the intrinsic region also electron hole creating. Okay, in this P region also electron holes are creating. So as usual in P type region, in the bulk regions, these are recombining. Okay, these are recombining. But here we have a large area in I layer. Suppose we will take a, instead of earlier we have only limited depletion width area, but here the depletion region is extended throughout the I layer. That means I layer area, how much I layer is there, that much of electron holes are creating here, that much of electrons holes are creating. So after creating here, and here electric field also existing in the depletion region, this total region electric field also existing. This electric field immediately separate these electron holes. Okay, this will send, these holes will send to P side and this electron sent to N side. Okay, that's why here inserting I layer, active area is increasing. And if active area is increasing means if you shine the light, if you illuminate the light, more number of electron holes are creating the I layer or depletion region also. These electrons holes are, and if in inserting I layer, internal electric field also existing throughout the I layer. Electric field also increasing. By inserting I layer, active area increasing first thing, or you can say depletion region increasing, and electric field also increasing. Because of this increased electric field, whatever electron holes generated in the I layer, that is intrinsic layer, immediately separate. First we generated electron holes by light. After second step is to separate these electron holes. So like similarly last PN photodiode, whatever electron hole generated in bulk region, that will recombine because there is no electric field, only electric field extended throughout the eye layer. So here whatever electron holes generated here, it will separate immediately by existing or developed electric field in the depletion region. Okay, that is why here more number of electron holes creating more current we are producing using PIN photodiode. Okay, if more current is producing means that means responsivity is high, and also here quantum efficiency also high, and also here see the bulk region is compared to intrinsic region, bulk region is smaller. So recombination loss also reducing because extending intrinsic layer. Okay, in extending intrinsic layer. Okay, just you compare, just we'll compare the two regions. Okay, suppose this is a P and region. So suppose we draw the electric field profile. Okay, just like it is a, it will extend like this. This is the, suppose you take this interface as a electric field profile. If you take PIN photodiode, the electric field profile is like this. Okay, it will be like this. So this is the I layer and this is P and N. Okay, so this is the I layer and this is P and N. Okay, so electric field profile at the at the center here maxima at PIN photodiode. But PIN, what is happening here? The electric field is extending throughout the eye layer, and here depletion width also higher. So see, just I am writing here. Okay, in PN photodiode, depletion width is smaller. Okay, depletion width is smaller. Just I will compare then. So if you draw the band diagram also, same thing you can write. It's not a problem. Okay, just I will explain. Just a second. So main thing is here. Suppose here you take PN and PIN. So in PN, depletion width is smaller. Here depletion width is high. Internal electric field also less. Here internal electric field is high. Okay, and you can extend the active area. Active area also high here. Active area is large. Active area is large compared to bulk regions. Active area is less here. Active area. Okay, active area is less here. Okay, so and also responsivity and quantum efficiency is less or low. You can write here responsivity, quantum efficiency, or you can write eta are high. Okay, are high, and also current is high in PIN. Current is high. Here current is low. Okay, these are the drawbacks and advantages using inserting I layer in between P and N layer. We can increase the depletion width, that is active area. That means if active area is increasing means more current will be generated, that will be separated by increased electric field. If this is separated after separation, that means recombination loss is also reduced and current also increased. If current is increasing means responsivity is increasing, quantum efficiency increasing. These are the advantage of using PIN photodiode. And also the circuit diagram and IV characteristics are same. You draw the circuit diagram, this is same as like we have drawn per PIN photodiode. Okay, why we are putting inside arrows means we are using photo light. Okay, this is minus and this is plus. Okay, here you can connect one ammeter. Okay, using ammeter you can measure how much current is flowing, plus and minus. This is series resistance. Okay, resistor. So this is negative and reverse bias. Always this will work on under reverse bias condition. Okay, this is same as, okay, same as circuit is same as, and same as like a PN photodiode, and characteristics also same. Okay, dark, this is dark current. Okay, when dark current means without any light on the device. Okay, when you shine the light, the current curve will be shifted down. This is light or under illumination. Okay, so this is VOC. You can write this is ISC, maximum current when device is shorted, maximum current flows to the device. and if you increase the intensity, light intensity, okay, light intensity. So here also current will increase. Current will increase. Okay, that is the same thing. Same thing. Same circuit diagram. Same IV characteristics. Same equation. That current equation we have written yesterday. Same. But here compared to PN photodiode, here current is high, responsivity high, active area is high. Okay, so this is the main region of increasing responsivity is increasing the adding the I layer, intrinsic layer. We are extending the active area and electric field. Okay, that is the main thing in PAN photodiode. Is it clear to you, everyone? Why we need I layer in between? Why we need? You got it right point?
Yes, sir.
Okay, okay, right. So this is I am just electric field profile I am drawing. So this is electric field. Okay, electric field, and in PAN photodiode this will extend like this. Okay, this will extend. Okay, so this is the width, or you can say, suppose this is the depletion width. Okay, in PAN photodiode, electric field is extended throughout the I layer. Throughout the I layer, this much I layer is there. Throughout the I layer, this will extended. But in PAN photodiode, this is P and N. The electric field is just like this one. Okay, here P region and N region. Okay, this is the depletion region. Here it is smaller, right? So compared to PAN, here P and N region electric field is less. You can see these two diagrams. Here first diagram, electric field is extended throughout the I layer. This is total I layer. This much is total I layer. Okay, so electric field extended throughout the I layer, and but here there is no I layer. That means electric field is only possible up to depletion region only. Here depletion region is small. Here depletion region also high. Okay, that is the advantage of adding intrinsic layer. And the construction we will see same construction also same thing. First we will take a N type layer here, N layer. After that, we will take little thicker I layer, little thicker I layer. This is I layer. Okay, I layer. After that, we will deposit again P layer. Okay, this is just like a NIP, or you can construct downside PIN also. You can NIP or PIN, whatever you can take. Here there is electrodes, two electrodes again, and backside also two electrodes. This front end, these are some metal contacts. Okay, a downside also metal. Okay, when you shine light here, okay, when you shine light here, in this I layer electron holes will be created. Okay, in the I layer electron holes will be created. Here electric field is existing, developed already. This electric field holes will send upside, only holes, and electron towards the n side, only holes towards the otherwise I will draw a little bigger diagram, then it is clear to you. So here this is a first we will take down, first we will take n layer. Okay, sorry, n layer, after that I layer, and here P layer. Okay, P and n layer thickness is less. Thickness is compared to I layer. I layer is generally will take 300 to 500 nanometer. 300 to 500 nanometer. This P and N like just like a 20 nanometer around. Okay. So here electrodes and top and bottoms are electrode. Again, can make it electrode. So using different techniques, that is no need here. Okay, when you shine light, electron holes will be generated. Here, whatever electric field is, it will send holes to P layer and electrons towards the N layer. Once this electron, first we are creating electron holes by light. We are shining light and creating. After that, using electric field, we are separating. Once we separate using metal contacts, we are collecting these electron holes. That is the construction of the device. Okay. Okay, tomorrow we will see remaining part. I mean, closing this session. Okay,